Good day, and welcome to Africa Team Geek. My name is Nonkululeko Madondo, and if you have just joined this classroom, this is a physical sciences class. My name is Nonkululeko Madondo. I am your teacher for grade 12 physical sciences. I hope that everybody is doing good and doing all the problems that I've given you guys to take as homework and do it for your own selves, just to sort of like uplift you into all the problems that we're doing. As you guys know, we started off from the top. We started off our lessons with some mechanics. We did some momentum, and we did some vertical projectile moment. So what we've done so far, we've done all of the term one revision. Okay, so today is going to be the last part of our revision for term one. We're going to be doing our matter, material, plastics, and polymers. This has actually been quite a lot of work because I think we've spent three Saturdays doing metals and materials. And remember, guys, metal and materials falls under your paper two work, and the other work falls under your paper one. So all the mechanics stuff is going to be paper one, and all the chemistry stuff is going to be paper two. We've done organic molecule, we've done organic molecule properties, we've done um, organic molecule, organic reactions, and now we're doing plastics and polymers. It's quite a lot of theory with this. I couldn't join in with the other lesson last week, so I had to make its own thing. But we're going to be done with term one work today, and next week we're going to starting over with our term two work. Okay, so we're slowly doing our revision to get ourselves ready for all the exams that are coming up, and just to make sure that you guys still remember what needs to be done, what does not need to be done. But for grade 12, we know that there's no amendments that have been done with regards to the work or the ATPs. It has not been adjusted. Everything still has to be the way it is. So we're doing all the work basically. That's what it means. And I hope that you guys are spending a lot of time doing your work, especially the parts that have calculations, because with calculations, it all goes with practice makes perfect. If you do not practice your problems, you're going to have a lot of problems, especially in your exams, because you're going to be making a lot of mistakes. So you need to make sure, grade 12, that you understand your calculation and you are very fond of it and you get used to it. So in a week's time, if we do the lessons that we do here, you can spend an entire week doing different problems from different examinations with your workbook or your papers that we are doing. But in this case, with plastics and polymers, it doesn't appear all the time in your exam, but when it does, it's very important that you are aware, especially in things like the multiple choice. They tend to drop questions like that. But remember, it falls also on organic molecules. So it can be asked in any form. It can be asked within a question on your exam papers, or it can still be asked with your other organic reactions because it's also some sort of a reaction. Okay. So reminding you guys that here I work from two very prominent textbooks. I work from Siyavula textbook, and I also work from the Study and Master textbook. So you have either one of them or any other CAPS approved textbooks. You can just go to the part that speaks about plastics and polymers, and you can follow through the work that we're going to be doing. So what are we going to be doing today? I see that I haven't really updated properly my content. Just for you guys to know, we're going to be doing the properties of polymers and plastics. We're going to be doing some examples. We're going to be doing the names, the types of polymers, and the type of reactions that you'll find from polymers. And we'll also do some exercises. And hopefully, we'll still have a chance to do an experiment if everything goes well. Okay. So for now, we're just gonna get started. So before we go far, there's just some few terminologies that we need to know when it comes to this part of the work. And these are the type of things that you're going to see occurring quite a lot as we move into the lesson. Okay, So the first thing that you guys need to know or might find is macromolecules. What are macromolecules? In this definition, it's a molecule that consists of large number of atoms. Okay, so it means that it's a molecule that has large number of molecules, like many atoms inside its molecule. Okay, so that would be a macromolecule. So basically, it would also be a large molecule. Okay, so another thing that we also need to know is what is a polymer. Since we're doing plastics and polymerization, a large molecule composed of smaller monomer units covalently bonded to each other in a repeating pattern. Okay, a long chain of repeated pieces made by addition or esterification, often called plastic. So a monomer means it's only one part of the component, one piece of component that is found in a large polymer. Okay, so you find this one monomer, like for example, we have it here. It shows this is our monomer, right? Just two, one molecule, and once it becomes a polymer, that's where it's extended. Okay, it's extended. It's got probably like a long chain of this ethene. Okay, so a monomer is small organic molecules that can covalently bond to each other in a repeating pattern. Okay, so you see these terms are more or less the same. The monomer is a small organic molecules that can be used or bonded covalently with each other in a repeated way. So which means that if you have ethene or you've got maybe methane, you can add many methanes and that becomes a polymer and they all get bonded together covalently, and with a that becomes a polymer. But what have you added? You added small organic molecules, in this case called ethene, and ethene is what is our monomer. Okay, I hope that you understand the difference between the two. Let me just show a highlight there. So you see, this is our monomer, so which means that ethene here is our monomer, and the polyethene polymer. So you see what gets added. You had your ethene, so once it becomes a polymer, you just add the poly in front of it, and it becomes a polythene polymer. And there's the N. The N basically represents that it can be a large chain. It could be 5, it could be 6, it could be 2, it could be any large number that could be required there. So if you check here, it says polythene polymer, and here we've got ethene. So what we've done, we've just added the poly and ethene and the polymer. So this is how the naming goes along. But you're going to see as we go into the lesson, it's going to start making a bit more sense. Okay, so make sure you know the difference between your monomer and your polymer. So the next one is polymerization. So what is polymerization? We've already spoken about polymers, and we've spoken about monomers being a long polymer, being a large chain of monomers composed together and bonded covalently. But what process is it that allows for that? That's where we get to the naming of polymerization. So that is the chemical reaction in which monomer molecules join to form a polymer. Okay, I think all of this could be much simpler to remember, but make sure that you still remember it and know all this work, because you will need all this work when it comes back as we go on to the lesson, and you'll see how it joins with the theory that we have learned on this part. Okay, so the first part that we're going to speak of is classification of polymers based on source of origin. Okay, so now what we're doing here, we're classifying them according to where they are found. Okay, so you might find others in nature, you might find others in laboratories, So that's basically what it means there when they say classification of polymers based on source of origin. Okay, so the first one that we're going to have is going to be a natural polymer. So that's the first classification of polymers based on the source of origin. So it says here, the polymer that exists in nature are natural polymers. Okay, so those are the natural ones, the ones that were not created by anyone except for God. God is the one that created them. You found them there, you leave them there, you use them, they become raw material, anything. You know, those are what we call our natural polymers. So in plants or in animals, that is, these polymers are called natural polymers. So we can differentiate it into 1, 2, 3, 4 parts of natural polymers and their occurrences. Okay, so it says here that the first one is a starch. Obviously, a starch, you might create it by eating certain food, but starch creates itself. It's a process that happens involuntarily in your body, and it happens automatically. So that is a natural polymer. So the main reserve food of plants. Okay, so it might be the main reserve food of plants, but we as people also need starch in our bodies, and we also happen to eat it. Okay. So number 2 is a cellulose. Cellulose is a main structural material of plants. Yes, cellulose is what protects the plant and what makes it moist, etc. So that is also a natural polymer because there is nobody that got to create it, but it was created on its own by itself as a process of part of the plantation. Okay. So moving on to number 3. Number 3 says protein. What are proteins? It acts as a building blocks in animals. And I know, guys, please don't get shocked when you see animals. We also fall under animals as human beings. So we also need proteins. Animals need proteins. Insects need proteins. So every living thing needs a protein, and it acts as a building block in animals. So this is what allows us to grow and our bodies to be very digestive, etc. We need the proteins. Okay. So number 4, we've got the natural rubber. So what is a natural rubber? It occurs as a latex in the bark of many tropical trees. Okay, so there's that latex part of a tree, and that is our natural rubber, especially the Hiva brasiliensis, a colloidal dispersion of rubber in water. Okay, so we'll get to see some of those as we move into. But it's very important, guys, that you know your different types of polymers and how they are classified according to the origin. Okay. So now we come to this question. I wanted to ask you guys, can you spot the polymer that is not a natural polymer here? So we've got the first one there. It says cotton from plant is, I'm just getting my highlighter. Okay, so cotton from plant. So already we've got something that's written there that we can take with us. Cotton from plants is a natural polymer and is used to make clothing. Okay, so why is it a natural polymer? Because there is no man-made formulas or laboratories that is required for this cotton to be made, but the plants make it naturally. Okay, so they produce it naturally, and we human beings go and steal it and try and make clothing for ourselves. Okay, don't mind that. But basically, that's what I mean. That cotton is made by natural means. Okay. Okay, and then let's look at number 2. We've already spoken about the natural latex from rubber tree is also a polymer. Okay, so there you see it. There's the natural latex. You can see all the juice coming out and pouring into this bucket. So that's the natural latex from rubber tree. This is also a polymer. So is this one a natural polymer? We don't know. Let's continue. A, cru a crustacean shell. is made of chitin. Okay, so there's a shell. You know, if you love seafood, you might have bumped into this in one of your dishes. So this shell over here is made out of chitin. Okay, a natural polymer as well. Okay, so where is our object that is not a natural polymer? Let's continue. If you do have an answer for that, however, you can send me a chat and I can go through it and see what you have done. So the next one, we had cotton there, but remember we've got silk. Silk from silkworm is used to make cloth. So do not confuse silk and cotton. They're both very different, okay? So the silk from silkworm is also a natural polymer. Why? Because it's created by small animals. It does not need any chemical or physical workshop for it to be very operational. Okay. And now we move to the next one. So we're done with silk. The next one, it says rubber can be used to make tires. So we can also use rubber to make tires. We can use natural toys to make tires. Okay. Natural rubber can be used to make tires. Sorry about that. So there, this one here, you can see all of this is rubber. Okay. So you can use this to, you can use that rubber to make tires. This rubber is our polymer. Okay. Okay. So rubber obviously is also our natural resources. Okay. So carbs like spaghetti are natural polymers. So they are natural polymers because these are carbohydrates that you get within the food. These are carbohydrates that are going to work in your immune system and your digestive system. Okay. So that's why in this case we are making it fall under natural polymers because indeed um, we're not talking about the spaghetti, we're talking about the carbohydrates that is found inside the spaghetti. So that is what we are looking for right here. Okay, so moving on to the next one. It says wood is a natural polymer used for paper. As you know, you've got your big factories like SAPI. What does SAPI do? SAPI is a pulp and paper manufacturing company. So what happens there? Why do they need wood? There's a certain type of pine wood that is used to make paper, and that is a pine wood that is used um, by these companies to make paper. So we need to get paper, you need wood, and there is many places that you can find in there around Pumalanga where there's a lot of pine plantation, especially with the sappy ground. There's a lot of pine plantations. This is because that is what is used to create the paper, and there's many other what's this environmentally friendly trees or things that can also be used by SAPI. So once you go there or you get into the company website, you can see all those things and how they are operated. Okay. And now we move to a rubber band. A rubber band, a rubber band. Okay. So if you take this rubber band, there is no way that this kind of rubber band is made from nature. Definitely, this rubber is made by somebody or a factory or a machine because you do not find rubber like this in nature. So which means that this rubber right here is what we would have as our this rubber here. Now we're going back to the question. So you see how easy it is for you to answer a question when you understand the how to answer a question when you understand what the question actually says. So that's the most important part for us to understand the question. So this one is the one that is not a natural polymer. So moving on, it says protein from eggs and other foods are also natural polymers. Why is that? Because eggs, no man is creating eggs. Okay, nowadays, artificially modifying, they can do that. But on a natural basis, trees can be used to make, eggs can be used to eggs form protein. And that's why you'll find that people that work out a lot and do a lot of exercises or bodybuilding, they drink a lot of eggs because eggs have a lot of protein and you require protein if you want your muscles to grow, etc. Okay, so that's why it's also a natural polymer. Okay, I hope that you guys enjoyed this little short mini exercises just to get you guys on the roll and running. Guys, it's very important that you understand this thing. I mean, if you can just understand this question that has been written here, that means that you already have insight or a mindset with regards to the stuff that you have to know about polymers. What's the difference between natural and other polymers that we're still going to read about. Okay, so the non-natural polymers. So we're going to move on to the second part of it. The second one is going to be our synthetic polymers. So remember, guys, first of all, we spoke about the natural polymers. So these are the ones that are found on everywhere on earth, things that is not created by man, but are created either by nature, by the animals, for example, like silkworms. It's the worms that actually create the silk. So those are all the natural resources that can be made by our that natural polymers that can be found in nature. So now we're moving to the synthetic polymers. Synthetic polymers, guys, is another word for synthetic polymers could be man-made, okay? Because there we had natural, now we've got man-made or synthetic polymers. What are synthetic polymers? Synthetic polymers are the polymers prepared in the laboratory and are referred to as synthetic or man-made polymers, such as polythene, synthetic rubber, PVC, nylon 66, Teflon, Orlon, etc. As you can see here, guys, I've brought in pictures just to give you guys an insight on the types of polymer. So you see, polymers is basically those thick rubbers, okay? Because this is, those thick plastics that are used to as containers or bottle containers or toys for kids and detergents. So these are things that you guys, I hope that now you slowly starting to understand what is what and where it all began. So the third one, oh my word, I forgot to put in a picture in here, but it's fine. We'll be able to explain it by words. So the third one, we have the semi-synthetic polymers. The semi-synthetic polymers means that it's half man-made, half created on its own. Polymers obtained by chemically altering natural polymers are known as a semi-synthetic polymer. For example, guys, we can go back to the stuff like a silkworm. A silkworm is going to make our silk. Our silk is our natural polymer, but once it's modified in nature to create something else, to create proper silk or to do the processing of what has been given to you, then we can apply that. Okay. These are polymers obtained by chemically altering natural resources. So once that has been, once you take the silkworm and it's modified or altered chemically so that it becomes a certain type of silk, then it will be our semi-synthetic polymers. This examples of this one is cellulose acetate and vulcanized energy. Okay. I hope that we're all good to go. So we've got three classifications of polymers based on the source of origin. The first one we did was a natural polymer. The second one is synthetic or man-made polymer. And the third one is semi-synthetic polymer. Okay. So that's what we added there for this lady. Okay, now moving on. It says here, moving to the second part of our classifications. So now they speak about classification of polymers based on the structure. So there we did on based on the place of on the origin, right? So now we do on based on the structure. So once you look at the polymer itself, okay. So the first one that we're going to look at is linear polymers. So these are polymers that bind the monomer units to each other to form long linear chains. Okay, so here they found it individually and want to make sure that they study all of it. Okay, so they are tightly packed in space by these linear chains. They've got high densities, tensile strength, and elevated melting and boiling points arise from close packaging. Okay, so guys, please, if you try and almost forget, the polymers, just think of the property. Just think of a plastic, and what is the weakness of a plastic? Obviously, heat. Heat is the weakness to a plastic because it's gonna melt and it's gonna burn out. Okay. So for example, a linear polymer are high density polythenes, it's nylon and it's polyesters. Okay. So that polyesters, you see polyethylene. Polyethylene, it means that this is ethylene extended. Okay. So you see this is ethylene and this is ester. Okay. Is an ester. So you can see already there, we've got terms of things that we've already been working with. So one of them is an ethene, but because it's a long chain of many ethenes joined together, it becomes a polyethylene, and it goes on like that with the esters. So which means that there's one ester, but now there's one ester repeatedly connecting into the same position of your other material. Okay. So this is how it's going to look like. There's a picture over there that shows our linear polymers. Okay, so now we're moving to the second one, which is the branched chain polymer. So we had our linear polymers, which are the ones that each unit form a long linear chain. And you check here, guys, remember with a long linear chain, with polyethylenes, is just one long chain of hydrocarbons. Okay, so that's why they mentioned that it's long chains. Okay, long linear chain. So on our second one, we've got the branched chain polymers. How do branched chain polymers work? It says in such polymers, the monomer units are connected with a source from to form long chain with some branch chain of the various length. Okay, so these polymers are not densely packed in space as a consequence of branching. They therefore have a poor density, low tensile strength, and a low point of melting and boiling point. Okay. Okay. So that's our picture. right there. So low density, an example of this would be low density polymers, starch, glycogen, etc. are some of the typical example of such polymers. Okay, so low density polythenes. But if you check here, let me just get a different color for our highlight. If you check here, when we did our linear polymers, here we spoke of a high density polythene, and here we're dealing with a low density polythene. Okay, so that's a difference. We've got our linear, we've got our branched. Our linear has high density polythene, and our branched chain polymers, this will have low density polythenes. So what will happen here basically is that we will there you're going to have a long chain, and there you've got a branch chain. So moving to the last but not least of them all, we've got our cross-linked polymers or network polymers. So these are the long ones that do not conform by any given space. They do what they do. Okay. So in such polymers, the monomer units are connected with the source to form long chains with some branch chains and various lengths. Okay. So in such polymers, the monomers units are connected with the source to form long chains with some branch chains of various lengths. So do we have it there? The monomer units are connected with the source to form long chains with some branch chains of various lengths. So it could be different ones. For example, if you have three of them, maybe you're mixing an ethene, and you also have something with a 1-methyl butane, for example, and you join them together. They're all of various lengths, right? They're not of equal lengths. So they're going to give you a different or weird structure, basically. They say here such polymers are not densely packed in space as a result of branching. Okay, they can't be densely packed in space as a result of branching because there's many of them and they all are bonded together covalently and properly. So they therefore have poor densities, low tensile strength, as well as low point of melting and boiling point. So once again here, we've got the low density polythene, such glycogen, and so on are some of the typical examples of such a polymer. Are we together? So now we've mentioned our three classifications based on structure. We've got our linear polymers, branch chain polymers, and we've spoken about the cross-linked polymers. So this one basically is a mixture of linear and branch chains, okay? Because others are linear and others are branch, and it all becomes one thing that we know as cross-linked polymers or network polymers. So now we're moving on to classification of polymers based on mode of polymerization. So there's many different modes of polymerization that we need to know and understand. Okay. So the first one that we're going to talk about is our addition polymers. Okay. So you know, guys, that in polymerization, it's a process where monomers join together to form polymers. So within those structures, all these polymers that we've spoken about, we need to always know what type of polymers these are, because you could have ones that are adding together to form one long polymer, or you can have one polymer and the other one is added onto it, okay, or removed. Or you can find two polymers, two monomers, and each of them get minus to form a long strand of polymers. Okay, so polymers that are incorporated have the same analytical formula, or we can say the empirical formula, as their monomers. Okay, polymers formed by the polymerization of monomers, which contain double or triple bonds. Basically, now we're moving to our unsaturated compounds, are, are referred to as polymers of addition of polymers. Okay, so polymers that are incorporated have the same empirical formula as their monomers. But I hope you guys still remember empirical formula from grade 11 when we started. But we're still going to do a lot of empirical formulas as we advance into other chapters and other terms work. Okay, so just make sure you bear that in mind. Empirical formula, we're still going to learn more about it as we move along. But we're not going to dwell much in it here, because here we're basically just outlining or talking about the polymerization. You need to start everything from the start. Okay, so the addition of polymers can be further divided into the following two groups on the basis of the forms of monomers. Okay, so now they talk about two types of group of addition of polymers. Okay, so the first one is homopolymer. So the polymers that are obtained by a single method of polymerization is homopolymers are called monomers. Okay, so what do they mean here? They mean that it's something that it's plain and simple, straightforward. You just repeat the same pattern or the same monomer over and over again. So it becomes a polythene polymer. Okay, so you're going to break those double chains and it's going to be bonded on the outside, as you can see there. We had our double bond here that's holding our ethene together, but now because we are making a long chain polymer, there is it. This is the double that we have. This is the double that we had from there. Okay, okay, I hope that this is not too confusing for you guys, but basically there is our additional homo. So here we had our ethene, which had a double or triple bond, but now because we are adding more of the ethenes together, we're going to break the bond and it's all going to be single bonds. That's why it's a polythene polymer. Okay, are we good to go, guys? So on that was A. Our A was our addition polymers. So now we move to our B. Our B is the polymers obtained by polymerizing two or more monomers that are known. Okay, this is known as a copolymers. Okay, so let's see now. So you see, before on the homopolymer, we were just polymerization, polymerizing one thing. Okay, so it's homo, it's one. Obtain a single method of polymerization, and we were only doing a thing. But now, once we get to the copolymers, is where we find two or more. Okay, so now we've got butadiene, we've got styrene, we've got two of them, and they need to be added together. And when they add it together, so basically, there it's going to be added here, right? So what are we going to do here? Here, basically what we're going to do is we're going to open this bond here. We're going to open this bond here and we're going to put another one line there. Okay, so we've got our two H's there. Okay, I'm just trying to jot it down for you guys. Okay, you guys will just excuse me. My highlighter is not a very much of an artist. All it does is just highlight. So you can see here. So these double bonds here gets broken, and we've got our this double bond here gets broken, and we still have our single bonds there, and we're just going to have another bond to this one right here. Okay, so you see, I hope this is not too messy for you guys to understand, but I'm just trying to put as much detail as possible just to show how these two are joined together. Because you see the first part there, and then you see the second part, but sometimes it could be very blurry to kind of understand how were they joined together before it was created and they made a polymer out of it. Okay, so that's what we had. Well, we took everything the same. So this is our butadiene. It's still the same. But on the last butadiene, you can see that there is a double bond. So you break those double bonds into the sides and you parent and you take both of them. Okay, yes, sorry about that. You take the 1H, you've broken them apart, and the other single bond that you removed from here, that's the one that's going to join with this one right here. And this one is also now going to be a single bond because now we've added a new bond that opens up to join with the butadiene. Okay, yo guys, there's many um, names of chemicals that you're going to be working with chemistry. But trust me, you don't have to know all of them. Just know all the important ones that you've been told to remember, especially in class, especially in our term work as we gradually move to other terms. Make sure that you understand how this gets to be made turned into a polymer. Okay, so a polymer, as much as it's a long chain, it doesn't mean that you have to write out the long chain. You can just write the longest chain, and you can write your end there to show that if it could be any number, it could be 1 times 1, then this would be enough. But then it could be times 2. The n could be 3, the n could be 4. So if you're, for example, your n is 2, it means that you're going to write this one, and then on the end of it, then you're going to start again and write from CH2, and you write everything up until you reach CH2. Okay. I hope that we all understand and slowly opening up to. Okay, okay. So that is our copolymer. So first of all, we did our homopolymers. That's the one where you only take one. Okay, it's only one uh, molecule, and you multiply it basically. You make a long chain out of it. A copolymer is where you have two or more um, monomers where you join together, and that becomes your one monomer. And now you're going to have to make it a long chain of polymers according to the n number that is required. Okay. So first we spoke about our addition polymers. That's the first one that we spoke about today. But we also have number 2, our condensation polymers. Okay, our condensation polymers. So what do they say about condensation polymers? It says they are polymers produced by the monomer combination with the removal of small molecules such as water, alcohol, hydrogen, chloride, etc. Okay, so basically, this is one way you produce monomer combination with the removal of some molecules. Okay, so in this case, we remove water or we remove alcohol or we remove hydrogen chloride. Okay, so something gets removed in this reaction when you add both polymers together. Okay, so I want us to do quickly some examples from a book so that you guys can have a clearer picture of what is going on, because I know I was a bit confused as well. I would have been a bit confused, and I know a lot of students that get confused by that, not understanding, okay, removal of small molecules, what does that mean? So I've put together something from our Siavula textbook that we can use. Okay, and here we have it. Okay. Okay, let me just see where it starts. Here we are. Okay, so we're coming to the condensation, polymerization. They mention that this type of reaction, two molecules combined by means of a covalent bond. So all our bonds are always covalent, okay? And small molecules such as water is lost in the bonding process. So which means that as they bond together, there's some water or other materials that get lost. So nearly all biological macromolecules are formed using this process. So very important information, eh? So all biological macromolecules are formed using this process. So polyesters are some polymers that form through condensation polymerization. Okay, so which means the esterification process that is done for polymers, that one is also done through the condensation polymerization. So polyesters have a number of characteristics which make them very useful. They are resistant to stretching and shrinking. You guys see that? Yes, I say that they are. Oh, let's get and highlight over here. Okay. These are some of the properties of the polyester. It says resistant to stretching and shrinking. They are easily washed and dry quickly, and they also resistance to mildew. Okay, so those are the properties of our polyesters. Okay, so the resistance to stretching and shrinking. Okay, why is that? Because they are very stretchful. They are moldable. You can stretch them and they move back to their original form. They won't stay stretched or shrunk. So they stay in the original position because of their characteristics. Okay. So it is this reason that the polyesters are being used more in textile. So polyesters are stretched out into fibers and they can be made into fabric and articles of clothing. So in the home, polyesters are used to make clothing, carpets, curtains, sheets, pillows, and poly upholstery. Okay, so you see where all of this polymerization can be used. So these are all polyesters and it's quite pricey. So if you do have your money right, you can get yourself some good material of polyesters. Okay. So it says here, polyesters are a group of polymers that contains the ester function group in their main chain. This one is called the ester link. We know about the ester links. We've done them in our previous worksheets. Okay. So for a polyester, however, there needs to be a continuation of the chain. So this chain is we're going to add them together, right? After we add the two ones that are formed, then we're going to have the long chain of all of them. Okay. or you can have your bracket and you can write N at the end. Okay. So this requires the diol, which is two alcohol functional groups, and diacid, two carboxylic acid functional groups, as shown in the figure, or a monomer that contains both the hydroxyl group or the carboxylic group. Okay, so remember how that is done, right? Remember when we did our esters, we always needed to have our alcohol and our carboxylic acid group join together for it to form a ester. So come now, let's see how it's done. Okay, so this is what we're going to have. We're going to have our carboxylic group, which is this one here, and probably this R there represents the hydrocarbon chain, right? So the hydrocarbon chain on this side, and at the end we've got our hydroxyl group, which is the OH, and we're going to add it to the OH. So this one is our carboxylic group, and this one is our hydroxyl group. Okay. So you see OH, OH plus OH, which is our carboxylic group over there, and OH. Okay. So what are we doing now? So they say there with they mentioned there that when two monomer molecules combine by means of a covalent bond and small molecules such as water is being removed or it's lost in the bonding process. So you see here we have our molecules. It's this one plus this one, then it's this one plus this one. But if you check here, now we're losing our water, our H2O. So there we took H plus H is going to be H2 plus O. It gets lost. On the same part here, small pieces of H2O is getting lost. Okay. And then once we remove those H2Os, then we're going to have our esters, because now it's the COO, COO, COO. Okay. I hope that you guys understand. So we added these two together, this one, and then we still had to add this one to this carboxylic group and this one to that that hydroxyl group. Okay. So it's hydroxylic group and hydroxyl group, but in both cases there was water that was lost in the process. Okay, are we good to go, guys? Are we all understanding the condensation polymerization? Okay, just want to see if there's other examples. So there are many polyesters. The term polyester refers to polyethyl terephthalate, PET. Okay, no master pronunciation, so we say it the way it comes out right in any form of a language. Okay, so this one is called an ester link. So here's another one. Okay, so this one here is going to be ethylene glycol and terephthalic acid. Okay, so it's ethylene glycol and terephthalic acid. So this one is our hydroxyl. Let me see. So this one here is going to be our hydroxyl group. I'll just write it as OH. And remember that you guys know that OH is our hydroxyl group. And this one over the side, the terephthalic acid is our carboxylic group, right? So this is the acidic group, COO. Okay. And we know that for the condensation reaction to take place, you need to have an hydroxyl group and you need to have a carboxylic group. So you have the acid and you have your base. Okay. So this part is our basic and this one is our acidic. So once we join them together, they're going to form as an ester. So what are we going to do to form this ester? We're going to remove these H's. Okay. Remember we said we're taking out the pieces of water. Okay, here we're taking out some hydroxyl group, HH, H2O molecule. So the H2O molecule is lost there. So in the end, what we're going to have is we're going to have our esters according to this form. Okay, so from the alcohol side, we're going to have our O. Remember, we remove the H and we remove the H on that side. So it's going to be OO. And on this side, we remove the OH. And on that side, we also remove the OH. So now we've got two H2Os basically. So once we remove what has been circled there, then we're going to have our carboxylic groups like this, okay? And this is our acids, okay? I mean, this is our esters. So this is how it's all going to work out. Guys, I really hope that you guys are understanding, because the main point is for you guys to understand what is going on. So this is how we work out this is how we're going to work out our esters, okay, our ester linkage. So all you need to remember basically is that when we do the esterification process, when it comes to the condensation, polymerization, you always have an alcohol acting with or a hydroxyl group that's going to be added to a carboxylic group, and with the removal or the loss of water in the process, okay. And that will give us our ester over there, okay. So polactic acid. So despite the name, the polactic acid actually is a polyester. It is an interesting polymer because the monomer used for this polymer comes from the biological fermentation of plant materials, while most monomers used in plastics come from petroleum. As a result, PLA is biodegradable and has a low carbon dioxide emission. Oh, great, right? Anything that has a low carbon dioxide emission means that it's ozone friendly, okay? So it means that it doesn't eat our ozone layer, so it's a good thing to use, okay? So once again, they're going to show us how the polylactic acid is formed using our diagrams here. So that's going to be the OH. There we have our OH, right, as an alcohol. The OH. Here we're going to take the OH, and here we're going to take an H. So here it's going to be H plus H is going to be H2 plus O, which means water is lost over there. So we remove the water. And on this side, on the carboxylic part of it, we're going to look at it. Here we're also going to take out the OH, and we're going to remove one H to make it H2O. So you remove water. So if you check on both sides, it means that here we've got minus H two, all right. And on this side as well, we've got minus H So you see, sometimes it's very important that you write your little notes so that you can remember them when you're starting for them, okay? So that's our condensation, polymerization, okay? So this is what the end result is going to be. So from the alcohol side, we remove these two, and this is all we're going to have there. And from our ester side, from our carboxylic side, we remove the OH on the side and the H on the side, and this is what we're going to have, okay? So it says here PLA is mostly used for packaging material, and because it is biodegradable, it has the potential to alleviate the landfill disposal problems. The PLA polymer structural repeats units given in figure 4.1.1. So this is basically our structural formula of the polyester polylactic acid. Okay, so when you talk about the polylactic acid, this is a type of group of polymerization that we are bound to have it. Okay. Okay, let's see. Okay, so here's a little exercise that we can also run into. It says in the question, which monomer was used? This is just to help you guys in understanding how to solve these polymer questions. Okay, a polymer, how are you going to identify a polymer or a monomer is things that have in a bracket and they have this in over here. Okay, that will make us know that okay, this is a polymer or a monomer, etc. Okay, so now they ask which monomer was used to make this polymer. Okay, so the monomer, if this was a monomer, you wouldn't have all these ones on the side. So this one, we would have a double bond there, and this one would be cancelled out. Obviously, this would be cancelled out, and you wouldn't have a bracket. Okay. So this is a it's a chloroputane, right? It's one chloroputane. Butene actually, because it's going to have a double bond, because a monomer is one unit. It's not many units joined together. It's one unit. Okay, so this would be a chlorobutene. Okay, because it's got double bond there, it's going to be in, not a. So it's chlorobutene. So number one, they say identify the polymer through functional groups. This polymer contains a chlorine atom. Which polymer contains chlorine? Is a polyvinyl chloride contains chlorine. Okay. Yeah, so this is a polyvinyl chloride contains chlorine. So on number step 2, now they ask, consider what you know of this polymer. PVC forms through an addition reaction, right? There are 2 carbon atoms in the repeat unit, ethane, and the polymer. I said butane is ethane, sorry, because it's 2, butane is 4. So this one is a chloroethane. Okay, sorry about that. I just got confused between 2 and 4. Okay, so it's ethane. Okay, so it says here PVC forms through an addition reaction. There are 2 carbon atoms in the repeat unit ethane, and the polymer contains a chloride atom. So now we consider what you know about this polymer. Basically, we know there is a chlorine there, and this is an ethane, and this is chloroethane, right? So apply this knowledge for the monomer. An addition reaction indicates that the monomer must contain a double bond, as the polymer contains units of ethane, and monomer must be an ethene. The monomer must contain a chlorine atom. So this monomer must be chloroethene, also known as vinyl chloride. Okay, remember we already mentioned it just by looking at it like this. We already knew that this is chloroethene. So there you have it. You have our double bonds there, which is our double bonds over there, and we've got our H's and we've got our chlorine. So after you name it and you say chloroethene, you have to draw the structure of this monomer. So once you draw the structure, it's going to be something like what we have here. So this is going to be our chloroethene, also known as vinyl chloride, but we always prefer to just use our structural or functional names because that is what we know. Once we start trying to figure out others, it's going to be a challenge for us, especially in an exam where you are so nervous and you just want to get done and you want to make sure that you write the correct answers. Okay, so just look at the structure and name it according to what we have learned in our other chapters. Okay. So let's come to another one here. It says here, which monomer was used to make this polymer? Give the name and draw the structure. So we already know here that we're going to cancel this one out. And we're going to do a double bond there. So already it's also got an ethene. So we know our suffix is ethene, right? So identify the polymer through the functional group. So this polymer contains benzene ring. So this is our benzene ring. Okay. This is our benzene. Guys, please do not judge my handwriting. Writing using this is our benzene. Okay, so this is our benzene ring. I've written it in such a funny way, but I'm just trying to make it easier for you guys to remember. Sometimes, you know, it's easy to remember that ugly handwriting that you made your notes on when it comes to test on an exam. So this is our benzene ring, okay? So we mentioned here that in order for us to make something that is connecting, we need to put our double bonds there, which means we cancel out these lines because this is a polymer. So now we're turning it into a monomer. We want our single unit. So, but we must have everything that was there. So this is going to be our benzene ring, and this is going to be our ethene. So it's going to we're going to have a benzene ring. So the polyester forms through an addition reaction. There are two carbon atoms attached to the benzene ring. Okay, so apply this knowledge to the monomer. So an addition reaction means that the monomer must contain a double bond. The polymer contains two carbon atoms attached to the benzene ring, which must be connected by a double bond in the monomer. So name the monomer. The monomer is styrene. Okay, you might not know what is styrene, but you will learn. So just know, for example, that you could have also written benzene ethene, right? Benzyl, benzyl ethene, benzyl ethene. Okay, you might write that in the exam if you're getting stuck, not knowing what needs to be done. But you remember, guys, that's the first time we come across the styrene. Okay, let's just go back and see in some of our work where we have our styrene, right? There we have it. So this is a styrene. Guys, just make sure you remember it. Once you study for your chemistry part, make sure you know some of the important ones, okay? So here we've got our styrene, which was also added to butadiene, right? So it's not quite difficult to remember because it's very similar to what we've already done. Okay, so there we have our styrene right there. Okay, so let's do another one quickly before we move on. I just wanted to have quite a number of problems because this one, they kind of like summarizing the difference between monomers and polymers and how to name them. So already now we understand that a polymer can be identified by two things. You don't have to have a long chain over here, but if you have these brackets here, oh sorry, oh, this looks terrible and untidy. If you have these brackets here, once they give you brackets like this, and it also has this end there, then we know that already what is given to us is a polymer, right? So what they likely to ask is for the monomer. Okay, so this is our polymer. So now they say give the structure of the monomer used to make polyvinyl acetate, okay, PVA. So consider what you know about this polymer. Polyvinyl acetate must form from vinyl acetate. So the IUPAC name of vinyl acetate is ethyl ethanoate. Okay, so you see, there's always an IUPAC name. So it's always okay if you don't know, like for example, the styrol. In this case where you didn't know the styrene, you can use the IUPAC name so that you can still get your mark and not fail to answer that problem. Okay, so this one is a um, ethanol, ethanoate. Okay, the polymer forms through an addition reaction. So apply this knowledge to the monomer. An addition reaction means that the monomer must contain a double bond. The only place in this bond can occur is between carbon 1 and carbon 2. So we can only have a double bond there, and then here we can cancel out the single bond on both sides. Okay, so this is what we'd have, and if you draw it, it would come up as this one. So remember, once it's in a bracket and has an N, then it's a polymer. But once it does not have that, then it's a monomer. Okay. Okay. So let's see. Okay. Let's just check if there's nothing that I've left out from this textbook here. Okay, so we'll come to this later on. Okay, so now we understand copolymers and how they operate and how they're added together and how the water is removed from each molecule. Okay, so I hope that that has made sense with all the examples that we have just taken part in. Okay, so condensation. Oh, I'm sorry, that was condensation. Oh, that was a condensation polymers where we learned that you can remove water, you can remove an alcohol, you can remove a hydrogen chloride, anything to form in this addition procedure. Okay, to form an ester. So before we go to this the condensation, I'd like us to go and look at some of the things that we need to learn about plastic. Guys, as you can see, all of this is part of your grade 12 work. This is part of your textbook. So plastics are light, cheap to produce, corrosion resistant, versatile, and can be dyed in any color. These properties have made plastic popular and that they can replace many conventional materials such as paper and metal alloy. So despite popular belief, plastic packaging does not fill our landfill sites. Analysis of the waste stream shows that plastic represents only 7% of the mass and 11% of volume by all waste. Paper represents 38% of mass by the waste stream. Plastics do not form toxic discharges and cannot pollute the landfill site. No water sources, no in the air with harmful chemicals. The inertness of plastics makes them effective stabilizers in the landfill. Okay, so the obvious option is to recycle. Here, we must consider the recycling cost in terms of energy used to collect the processed material and in comparison to the amount of energy used to make product from new material. So some plastics are more suitable in recycling than others. Thermoplastics, cool drink bottles made from PET can easily be heated, remolded, and recycled. Okay. So, numbering of plastics. It says each type of plastic needs to be specified, needs specific recycling treatment because the ways in which you treat each plastic is going to be different according to the properties that were used to form the product. So, to accommodate the recycling option, an international identifying system for packaging plastic has been introduced. Plastics are divided into 7 groups, each with its identifying number inside the logo. Okay. So these logos are molded into the plastic, usually in the base of the plastic. Okay. This will be heated at low temperature to melt the polyester and remold the new thermoplastic product. Okay. So here we have it. And all the abbreviations. It says PT is polyethylene terephthalate, HDPE, high density polyethylene, and the third one is going to be polyvinyl chloride. This one PVC, you might have heard it a lot, and you're still going to hear it a lot if you're going to continue with physical sciences and chemistry on your studies. Okay. Then you've got LDPE. This is the low density polyethylene. Remember, I spoke of a low density when we started this lesson. Some of the ones where we mentioned property, others require low density and others require high density. So we've got polypropylene, and then we've got PS polystyrene, and number 6, it's going to be polylactic acid, multi-layer plastics, and okay. So the others, it could be e.g. polylactic acid, multi-layer plastics, and other engineering products. Okay. So these are just a few that I wanted to share with you. Okay. So we also have a recycling process, but we're not going to dwell much into that. Okay, the textbook is moving quite slow now. Okay, while that is still loading, we can go back into our Sia Vula textbook. There's also stuff that we can check out in there. Okay. So the impact of polymers and plastic. Remember, guys, we are doing polymers and plastic. So with the plastics, a lot we're going to be talking most about the environment and what they cause. So plastics and the environment. Although plastics have a huge impact globally, there's also environmental price that has to be paid for the use. The following are just some of the ways in which plastic can cause damage to the environment. Okay. So number 1, it's waste disposal. Plastics are not easily broken down by microorganisms, and therefore most are not easily biodegradable. This leads to waste disposal problems. Okay. And then the second one, we've got the air pollution. When plastics burn, they can produce toxic gases such as a carbon monoxide, hydrogen cyanide, and hydrogen chloride, particularly from PVC and other plastics that contain chlorine or nitrogen. So they can also, when they burn, they can also form a air pollution. They also contribute to air pollution when they burn. So it's very important that you make sure that you do not just randomly burn your plastics, because they cause damage to our system. Okay. So number 3, we have recycling. It says it's difficult to recycle plastics because each type of plastic has a different properties. So they are, and so different recycling methods may be needed for each plastic. Some plastics can be remelted and reused, while others often ground up and are used as a filter. One of the problems with recycling plastic is that they have to be sorted according to the plastic rule. Okay. Alternatively, plastic should be reused, and my main cousin, I mean, In many countries, including South Africa, shoppers must now pay for plastic bags. This encourages people to collect and reuse bags as they already have. Exactly. I mean, remember back in the times when plastic was free, we had a lot of people that used to waste plastic bags. So now that you actually pay R1 for a plastic, you are likely to take care of it and you're likely to use it only when you need it. So that was also another great thing that was done. Okay. Okay. So we should be done here. So I think now we can go to one of our problems. Hope that we're good now. Now we understand the plastic, the properties of plastic, and the effect that it has on the environment. So now we can move on to our problem here. It says plastic bags are made from the polymer polyethylene. Okay, so give the IUPAC name of polyethylene. Okay, so it's ethane, right? Ethene. Last time I checked. Okay, so the IUPAC name is polyethylene. Okay, so that's the IUPAC name. So once it says polyethylene, it means that now it's a polymer. But if it's a monomer, it's going to be ethene. Okay, so now they want us to give the IUPAC name and structural formula of the monomer of polyethylene. So polyethylene, remember what we said about polyethylene? We said it's the one that's like this. Okay, I'm just making a couple of mistakes, but I want to write it down so that you guys can sort of like understand. Remember, we know that every carbon needs to have four bonds each. We don't have more than four bonds. So in this case, we only have okay. It's going to be C. Okay. You know, sometimes guys, we need to think in a broader scope how we answer these questions. You always need to make sure that you store the structural formula before you even check what they want from the structural formula. It's really good. Mm. This is basically how it's going to look like, okay? This is our F, but because it's a polymer, mm, oh, this is the monomer. The monomer is like this, okay? So, show the structure of polyethyl by making use of the condensed structure formula, okay? So, how are we going to do that? There we have it. You see, so a theme is going to be like this, exactly how we do the other one, but with this one, we're going to draw a chain according to uh, what has been given. We got our polythene. We can put maybe two. We could have put three. We could have put four of the ethene joined together. Okay, but in this case, we've got one, two, three. We got three ethene. Okay, joined together to form a polymer. Okay. And then it says on our next question, name the phase of monomer and of the polymer of polythene at room temperature. Okay, guys, important question for a child. This could be asked at any given time, at any random question that have been asked in the examination. Name the phase of the monomer and of the polymer of polyethylene at room temperature. And that is ethene is a gas and polyethylene is a solid at room temperature. Interesting information, right? Ethene becomes a gas and polyethylene becomes a solid at room temperature. Okay. So moving on to the next question, which is number 2. It says use a structural formula to show the polymerization reaction between where is it? Between this one and this one. Already we can see what is going on here. This is calling for an esterification, right? So which means that now we are working on a polyesters, right? Because we've got our codes. Okay. Okay. Wanted to remember the condensation reaction. Remember what we said? We said we take H2O on both sides. In this case, we can take this OH here and we can take this OH. Okay, so now what they know, they said use a to show the polymerization reaction between this one. Okay, so this one is not going to be hard to decipher because you're just going to draw it according, you're going to make it a branch structure like this one here. And now what they want to know, what is the type of polymerization reaction called? This one is a polyester, right? Is the ester linkage procedure. Okay. Okay, so here is it where we draw it. But remember what I said. It's going to be N times H2O, N times H2O, and this is going to be our condensation reaction. Remember, we spend a lot of time doing the condensation reaction. That's where condensation reaction, or you can also say the esterification reaction, okay? Because with the esterification, that's where we remove the water from the water, okay, from the molecule. So we're going to add these two, and then it's going to give us this one, okay? And then for it to be a polymer, you have to write down the brackets. Okay, so condensation reaction. Okay. So what they wanted to know, which inorganic product also forms during this reaction? Remember we mentioned that a carboxylic and an a hydroxyl and a carboxylic uh, and a carboxylic group act together, and once they act together, once they react together, they form an ester, and they also during this process we know that water is also lost. That's why I mentioned there that we're going to have our HOs and our H2Os removed from both sides of the group. So another which inorganic product forms during this reaction? This will obviously be our water, because water is inorganic, and that is what we get, which is lost in the condensation polymerization reaction. Okay, so moving on, it says consider the polymer A to C on the left. Give the structural formula of the repeat units for A, B, and C. Give the structural formula of the repeats. So once you put repeats, you just put them in the bracket and you put a small n at the bottom of your sheet. Okay. So that's most important for it to be a polymer. You draw your monomer, add it together, but then you add those brackets on the side, the square brackets on the side, and a small n at the bottom to show that it is now a polymer. You just took a picture of a piece of a long strand of material that are acting together. Okay, so number B says give the condensed structural formula for the monomer A, B, and C. Okay. So there we have our A, B, and C. Okay, got our A, B, and C. So there's our PVC on A, B. There we have it, polystyrene, and C, polyvinyl acetate. So what they want to know, give structural formula of the repeat units. So for the PVC, it's going to be, now we're looking for the monomers. Okay, 1, okay, so this is our monomer. So we're going to have it as a repeat, because there you see the chlorine. Always best to start where the unwanted is. Okay, so there you have it. Okay, A, B, and C. But I think it makes sense. So you see this one, we didn't write the repeat, we just put it in the bracket and then wrote the small n there. So it also makes sense. So the polystyrene, um, we just add stuff that we be doing for. Okay, so now we've named them, right? So give the condensed structural formula for the monomer. So which means by condensed, they mean that now they want it to be brushed out properly, like the H's must show on each side and not written on this nature. Okay. And this is what how you would have it. Okay. So this would be our condensed structural formula for the monomer. Okay. So, I made a mistake here. I'm sorry about that. I just lost track of my screen share. but I'll get back to it just now. Okay. Okay. So given the condensed structural formula B, we already sorted that one out. These are our condensed structural formula. Remember I told you guys with the condensed structural formula, do you guys see that there's many ways in which you can show your polymer or your monomer? This one already makes sense because you can see here, this one here is what depicts to us that this is a polymer, right? Sorry about that. So that's how you identify. So you can either identify it like this or when it has the brackets, okay? So when they want it to be condensed, it means that they don't want it to be written CH3 or CH4. They want you to condense it, to structure it out, the carbons and the hydrogens, write them each individually according to the way they're supposed to be, okay? And then B, you have it as well. There you have our polystyrene there, like we mentioned. Remember, polystyrene is the one that has a butyl group and an ethyl group, right? So this will be a butyl ethane. If it had to be an IUPAC, okay. And then the last one, polyvinyl acetate. We've also, you see this is NO8, ethanoate, because it's an ester. It's one that has been esterified. Okay. And then let's go to number B. Okay. So this is the structural formulas of each one of our polymers. Okay. And then the condensed part is going to be this one, where we have our CH, CHL, CH. You see, this is how we're going to write it down. Okay. But it's always much better if you draw the structure first before you're writing it out in words, because otherwise you might get a bit confused, especially with the number of H's that you need to draw or you need to write. So make sure that you do that. So we're moving on with other questions. It says on this question, on a number 16 question, it says explain the difference between the following terms and give examples of each: a monomer, a copolymer, and a homopolymer. Okay, so what do you know about these ones? Okay, there we have it. It says a monomer is the smallest unit in a polymer, which is repeated many hundreds and thousands of times. Ethene is the monomer in a, for example, ethene is a monomer in polythene. So you don't really have, oh, they said you must have an example. So ethene is a monomer in polyethylene. Okay. Okay. So the copolymer is made up of two or more types of monomers. Okay. So which means that it's an addition reaction whereby two monomers are added together to form a product. Okay. To form a long product. And that product is what we're going to turn into a polymer. Okay. So this is an addition reaction. It's an addition reaction, okay? So made up of two or more types of monomers, e.g. polyester is made from the monomers tetraphthalic acid and ethylene glycol, okay? You see, it's always theory that is coming back, things that we've gone through theoretically, that is now tested to each one of you guys, okay? So a homopolymer contains only one type of monomer. Okay, so they remember that's the difference between a homopolymer and a copolymer. A homopolymer contains only one type of monomer. For example, the polythene, right? That's where you only have an ethene, and when it becomes a polymer, you just add an N at the bottom, so it means that it can stretch to however long it wants. But when it comes to a copolymer, that's where you need to add two monomers together. You might add your polyphenol and your um, tetraphthalic acid, and you add them together, then they form this big monomer that can now be turned into a polymer. Okay, hope that it all makes sense, guys. If it doesn't, let's always shout out. Okay, so it says here on number B, explain why polymers are generally solid at room temperature. Explain why polymers are solid at room temperature. So it says here, polymers are macromolecules with large molecular masses. Intermolecular forces are stronger in large molecules and keep these in a solid state. Okay, the molecular forces are stronger in large molecules and keep these molecules in a solid state. Okay. So moving on to number 17, it says polythene is a widely used polymer. Name the monomer of polythene. Okay, we know that the monomer of polythene is the ethene, right? It is ethene because it's got two carbons double bonded with hydrogen. So it's a hydrocarbon with two carbon bonds, right? So they say, yeah, that's basically the name of the monomer of polythene. So name the type of polymerization process that produces polythene. It's going to be the homo, right? It's going to be the homopolymer. So now they say draw a diagram of these three monomers and show how they polymerize. Okay. The name the three uses of polythene. Okay. So yeah, that's the addition polymerization, like I've already mentioned. An addition because it's adding together, and it's a homopolymer. Okay, so the monomer ethene, there it is there. Okay, so there we have our monomer ethene, and then at high pressure heat, then we want to join them together now to form single bonds of each, right? So they break that double bond, the unsaturated bond will break, and they will form one long hydrocarbon chain. Okay, so the repeat unit can be summarized according to what we have there. Okay, okay. So now they want to know, name the three uses of polythene. So polythene could be our plastic bags, squeeze bottles, films, toys, molded objects, electric insulators. These are all part of the polythene material. Okay, so this is the uses of polythene. This is what they make. Okay, plastic bags, squeeze bottles, films, toys, molded objects, electric insulation, all of them. Okay. So it says on number 18, polyester can be used to make cold drink bottles and many other useful products, right? That's polyester. It is also woven into fabric. The monomer of polyesters are ethylene glycol and tetraphthalic acid. So this is what we have as our monomers that are going to be added together to form, added together and eliminate the water to form our our ester link. Okay, so name the type of polymerization process that forms polyester. That is a condensation polymerization, right? Remember we spoke about the condensation polymerization is the esterification polymerization. Okay, so it says name the bond that forms between ethylene glycol and tetraphthalic acid. That would be the covalent bonds, right? Those are the bonds. So write down the balanced equation using the condensed structural formula to show the reaction between ethylene glycol, and tetraphthalic tetraphthalic acid. So there you would have your normal structure the way you have it, but you will add plus H2O because H2O is also added, but write it as an N, okay, in the corner. So let's go and see our number 18. So you see, this is condensation polymerization. The type of bond is the ester bond, the ester linkage. Remember we spoke about the ester links that are formed in our condensation reaction, okay? Polymerization, I mean to say. So number C, there we have it. It says, there we've got our tetraphthalic acid. There it is, plus N ethylene glycol. And then at high temperature of 280 degrees with a catalyst, this would give us a large polymer. Okay. And this is what we have. Plus, I mentioned to you guys, we will have two products in the end. We'll have our polyester, but we'll also have our water, which is lost in this chemical reaction. Okay. Okay. So moving on to number 19. Number 19 says identify the monomers that are formed. Identify the monomers forming the following polymer chain and draw their structural formula. Okay, the monomers that are used here. So here, polactic acid, we already know one thing. We've got a hydroxyl group and we have a carboxyl group because there it is there. That's where it all gets broken down. Okay. So there we probably have an OH, right? But let's go and check it out so that later when it's viewed on our sketch. So you see what we have. This would be our thing. Like I mentioned to you guys that here, we would have to add our OH, which is this one here. That is added into the equation, and this becomes our monomer. Okay. So we added an OH, and that became our monomer. And then now we come to PVC. PVC will be the same thing basically. We're going to cut the line right here. Okay, and this would allow for a double bond over there. Okay. So there we have it. You see, this is a chloroethylene. So let's go to number C. I know they're quite tricky, guys, but once you practice and make perfect, you're going to see how easier it slowly becomes. Okay, it's going to become easier as you practice more problems at a time. You have 1 week to do all these problems and to understand them. I bet you, if you do that for yourself, you're not going to struggle with any chapter. Okay. So now we have our number C. Now this one also, you can see these ones are all the same, which means that our monomer breaks from Okay, so there we'd have it, right? We'd have something like this. So there we'd have our double bond there. And this would be our monomer right there. Let's go and check it out again. And number C. Okay, here they've just condensed it, okay? They've made it very, they've actually broken down so that it's not in the form that it's written in right now, but this is how it would be. Okay, so here if you have your C6, you know that you have 6 carbons going all the way up, and your 5 hydrogen bonds all around it. Okay. So going on number D. For number D is quite simple. This polythene is our simplest form of our polymer, right? That's where we cut it there and we add our double bond there and we break it up into the proper hydrogen levels, and this becomes our ethene, right? This is going to be our ethene. Let's go and check it out. So there we have it. It's going to be our ethene. It's this one right here. This is our simplest form of polymer, right? Okay. So now we move on. We go to number E. So number E is our PVA. Okay. PVA. So which means that our PVA, we're going to cut it right here as well, right? Because you see here, it's all the same as this one, the same as that one. And what we're going to do here, what we have right there, we're going to have our double bond. So once you have a double bond there, then it's closed up. It means that we have our monomer right there. Guys, I hope that everybody's following through and you're slowly understanding how all of this is working together, because it's very important that you understand how you decipher a monomer and how you decipher a polymer. You need to know the difference. You need to be able to see, like for example here, you can already see that this is a polymer because it's got a pattern. So you look through the patterns, they both have these two, they both have CHs, and they both have CH2. So what follows next is what we started with the CH. So always make sure that you follow the pattern, okay? Let's see it. So you see, there we have it there. We just closed our ethanol. There we put in our double bonds there, like I mentioned there, that we're gonna have our double bond. So this becomes ethanol, okay? So that means that's our monomer for PVA. So coming to our last question, it says, plastic products have become commodities of choice. Write down a paragraph on both properties of plastics that make them so suitable for use in our modern society. Very interesting question, right? Okay. So let's go and see what you should write when you get a question like that in the exam. First of all, what we need to know is that plastics are used in packaging for the following reason. Okay. So you can put that in a paragraph form, that in industry or in use, plastics are used in packaging for the following reasons. They've got good strength and elasticity. They've got durability. They are photodegradability, easily molded into shape, as you know, you can package it anyhow. They have low density. The low density gives light mass. The insulation properties, the hygiene or inert and safe, does not contaminate food. Okay. So corrosion and chemical resistance. So they do not corrode. You know that about plastic. They do not fall under corrosion, especially if they've been in contact with water. Water actually you can clean them with water, or and chemical resistant or certain ones. Okay, you know you do not put acid on your plastic; it will burn it out. So make sure your corrosion and chemical resistant, transparent, and allows us to see the packaged product. So it depends on what kind of plastic you're talking about. It could be a plastic container like the one that we had. There's this one that we spoke about. These ones you see, you can see right through them. Okay. Okay. So transparent allows us to see the packaged product, and they're very cost effective. You know, all plastic products are very cheap to use, and plus they do not break easily. When you drop down a plastic container, it's not going to break like a glass a plate would do. So those are most important features that you guys need to bear in mind when you write an essay about plastics and their use in society or throughout. Okay. So plastics are used for a wide variety other than other products because they are practically unbreakable and durable. When you drop a plastic, it will not break. A plastic container doesn't easily break. They're very they are very convenient to use, practical and breakable and durable. They are electrical and thermal insulators, so which means that they are not subdued by electrical shock. So you can put plastic in electrical shock. Basically, they even sometimes used as insulators. So plastics are very good at that as well. So they're electrical and thermal insulators. They put, as you can see, even the plastic kettles that we use, they also very highly insulated because you can hold the kettle and it will not electrocute it even while the plug is plugged in because it is insulated. Okay, so they produced in different colors. So which means by this part, they're talking about the different colors that you can have. You can have it transparent, you can have it different colors. The color able, okay? You can change them into different colors because plastics are just good like that. They're very convenient product to use in our daily lives and in anyone. So they're easily molded in different shapes and sizes. Okay. So which means that you can make containers, you can make bowls, you can make anything. You can make toys, you can make bottles, you can make plates, you can make so many things with plastic as you guys can think of in your daily lives, even at home. Just by where you're sitting, you can already see a lot of plastic products that are around you. So that's why it's easily molded into different shapes and sizes. Okay. And it's corrosion resistant because it's a plastic, it's not going to rot. Even if there's water on it, it will not rot because it's a plastic. The only time you'll have a problem is if you have acid and stuff. So here they just want to know the good uses of plastic. They don't want to know the negative part. They only want to know the good parts of plastic. But guys, we have reached the end of our lesson. My name is Donkulego Madondo. I am your physical sciences grade 12 teacher. Thank you guys for a beautiful classroom. We have closed a chapter on plastics and polymers. And next week, we're going to be moving to term 2 of our work. From me, Nonkulego Madondo, grade 12 teacher, goodbye and have a great day.